Well, welcome to DDD Europe, and thank you for the welcome. So today, my talk, I think the one I'm assigned is sort of what is domain-driven design. And so I'll try to get across sort of the basic concepts and the motivations, and then they'll go into more detail in some of the other talks about some of the important principles, as you've seen on the agenda. I always like to start the discussion with this statement. It's like a mantra almost that I do, because a lot of people come to design with deep-seated perfectionist tendencies, and those tendencies undermine all our attempts to do good design. And this I say as someone who has this tendency, and speaking to a room full of, I'm sure 90% of you have this tendency too. So keep that in the back of your mind as we go along. Now, there are a lot of people who don't have that tendency, and when they look at some of the things we do, and they'll say, you know, you don't need all that, and truth and beauty, it's just truth and beauty, and all you need is software that runs. And what we're doing is about software, right? Our goal is to create software that does an important job. And so what is the most effective way of creating software that does an important job? It isn't a given that that would be models or a particular style of doing models. That shouldn't be taken for granted. We should always be questioning our assumptions. But I think there is a good case for it, and I will try to illustrate that case with an example. All this stuff is so abstract. I like to get straight to an example. So mostly in this talk, I'll go through this. The example is from a domain of container shipping. This is for bulk cargo transport, and most people, I think, are at least a little bit familiar with this. Almost all bulk cargo these days is loaded into containers like this one, and then put onto ships like this to go across the ocean, transferred in ports like this, to go onto other ships or onto trains. You just simply attach a chassis to the bottom of the container and it becomes a train car, or a different kind of chassis, and it becomes the trailer of a truck. And so this kind of intermodal transportation, it's very efficient, and you can imagine it has some logistical complexity. And because of that logistical complexity, there's a lot of software involved. So I think that, well, anyway, so imagine that we work in a company, a shipping company, and our job is to write software that addresses those logistical issues. So a typical kind of problem, a kind of case that we might be looking at would involve, say, a customer calling one of our clerks and saying, I have a container in Hong Kong, I want to ship it to Dallas, Texas. So the clerk might say, all right, they put into the computer, the origin is Hong Kong, the destination is Dallas, and the computer will come up with a routing for that cargo. And then they will explain it back to the customer. All right, your cargo would be loaded in Hong Kong onto a specific vessel voyage. ABC is the designator of that in this picture. And then in Hong Kong, it would be transferred onto a train, XYZ, and that would get it to Texas, to Dallas, Texas, on a certain date and time. The customer says, all right, that sounds good, book it. So then they take a few more steps, and it's stored in the computer. This is our first use case. And we could start immediately thinking about, all right, what kind of objects do we need, or what kind of functions do we need? And we could develop a design and a model for this thing. But that ignores one of the realities of software development, and that is that we already have software that does this. In almost every project, we're working in a problem space where there's already a lot of software. Our software will have to coexist with that software. Perhaps we're talking about a refinement of the existing software. Perhaps we're talking about some new piece of software that will integrate with another piece of software. Or maybe we're talking about a new piece of software that's replacing a piece of existing software. But there's always existing software. Even in so-called greenfield projects, there's still existing software, and that's a very important constraint. So I don't like to ignore that constraint. And a number of the techniques that will be talked about later, some of those are related to that, especially context mapping. But for right now, we'll sort of assume that we are going to be refining an existing piece of software. So let's look briefly at the design of the existing software. So this is a very high-level view. And in this very high-level view, we can see that we have an object called a cargo, which is populated with all the information that the clerk would collect as they talk to the customer, especially the origin and destination of that cargo. Then they pass that information to a service called the routing service. And that service will figure out the steps, right? Which actual vessel voyages, which ships at which times, can actually take the cargo from its origin to its destination. And as it does that, it puts its answers into a database table called cargo bookings. Now, this design, which is fairly typical, I think, of legacy software of a certain generation, and it's not a bad design. It has one characteristic that's quite good, which is I can explain it at a high level very quickly and clearly. So I think everyone understands this high-level view at this point. That's a good characteristic. Not all designs have that. But it also has some drawbacks. And some of those drawbacks might be preventing us from adding features or improving features that we want to do. Now, when I look at a software design, I try to have sort of two perspectives. And I try to shift back and forth between those two perspectives. One perspective is the software designer, software engineer type of perspective. This one, I apply all the principles that, that we have learned about how to make software somewhat clean and changeable and so forth. For example, with this set of eyes, I might notice that there is a side effect here, kind of a problematic side effect, that as the routing service does its job, a very complex piece of logic, it is also updating the database. To combine complex logic with a database update is basically a violation of an old principle of the separation of the logic from updating state, and that's a principle that goes back before domain-driven design, as a name anyway. So I would notice that in other things. But there's another perspective I want to bring to it, which is the domain perspective. If I were talking about this design with a person who is not a software developer, but instead an expert in shipping, how would I explain it to them? And it would start out much the same as the way I talked about it with you. I would explain how you give the routing service an origin, destination, and a few other things, and then it will come up with the stops that the cargo will have to make and put them in the database. And at this level, communication is pretty good. A shipping expert would understand that, would understand these kind of components of a software system and how they interact. But we need to get a little more detailed than that. We can't always have such high-level discussions. Suppose I wanted to discuss an issue that comes up sometimes. I showed you an itinerary for a shipment that looks like a pretty good one, but sometimes, for various reasons, you end up with something like this. So notice that now the cargo is unloaded in Long Beach, California, and then loaded onto the train in Sacramento, California, which is hundreds of miles away. So how did it get from Long Beach to Sacramento? Well, it wouldn't. If we had an actual itinerary like this in the system, they would follow the instructions of the itinerary. When it arrived in Long Beach, they would unload it. But then when the time came for the people in Sacramento to put it on the train, they would look around for it and couldn't find it. And then eventually someone would figure out what had happened. But what we want is to be able to notice when this happens and take a corrective action. And people talk about this, and they talk about these kind of disconnected itineraries. But how is it reflected in the software as it exists? Well, it is there. We have some relational integrity constraints in the database table. But when I start talking about this and this solution, I find that I lose my connection with the domain expert. I can't talk about this with a shipping expert who doesn't really understand software that well. So we have to find another way of dealing with this, and a way that gives us a design just as clean and effective, but maintains that communication. So in these kinds of combining these two perspectives, this is how I want to think as I go forward. Now, I think about what concepts are we missing that we are using when we talk to the domain expert. We're almost shifting between two conceptual systems, between two models, two languages. So to find an alternative, we need to somehow get into a creative collaboration with these software experts. I mean, between the software experts and the domain experts. And that's not so easy to do. Sometimes you can get one of these people into a room and got a nice whiteboard, and you say, you know, like, well, what concepts are we missing here? And, you know, nothing will happen here. So the thing is that getting these conversations started is quite difficult. I'm going to talk about sort of the things I often do, kind of tell a little story of a typical way. But that doesn't mean this is the way it's done. And in fact, later in the day, Alberto Brandolini is going to talk about event storming, which is a technique that is, among other things, a great way to get a creative collaboration going between those two kinds of people, I think. That's I think, the most exciting aspect of it to me, actually. So, but nonetheless, here's kind of a thing that I do. Take this as a story about, you know, how it was done in this particular case. First of all, I like to go in with an idea or two, you know, to just kind of start feeding the conversation. And where do those ideas come from, though? Well, often, you know, you're just popping with ideas if you've been working in the domain. But one of the principles of domain-driven design is that the language is very important. And one thing I've noticed is that when we talk about our software, we don't use the same language that's actually in the software. So, for example, here, let's compare the way I talked about this system, even at the high level, with the way it actually works. So I said, give the routing service an origin and a destination arrival time. And if you look at the diagram, you will see that, in fact, that's exactly what happens. I mean, taking this diagram to be an accurate representation of the software. So far so good. And then I say that the routing service, the routing service, will look up the stops the cargo will have to make. Now the thing about that is that the word stops does not appear in the diagram. And we can do a little search of the code and so forth, and we will find that stops is never used in this way anywhere in the software. It might be in a label here or there. So this is a concept so basic that I use it to explain what the routing service does. What does the routing service do? It looks up the stops the cargo has to make. But that's not actually what's happening in the software, not at least in those words. So maybe here we have an idea that could feed the conversation. And so I could propose something. I could say, well, cargo, we already have the cargo object. Maybe the cargo object could have a series of stops. Now, I propose this, and my shipping counterpart says, yeah, that sounds good. Let's do it that way. And so I feel good that I had a good idea. Now we can take this, we can refactor the software, we can have a better communication between the two types of people and so forth, and never look back. Actually, this is often what happens. And that is another point where things can go awry, because at this point I will have lost a great opportunity. The first decent idea that came along is often the last idea, because we latch onto it and we stop thinking. As a metaphor for this, think of, or a comparison anyway, think of what you would do if you decided to go shopping for a car. You might do a little research and you'd say, okay, what do I need? And you'd write down some things you need. I want to have a sedan with enough room for 4 people and so forth. And so you go, and I'd like to have it be green. And so you go to a dealer. You say, well, these are things I want. I want a 4-door sedan. I want it to be green. And there are other constraints there, too. So the dealer says, all right, well, here's a car over here that is green, 4 doors. It meets all your requirements. And so you say, okay, I'll take it. Is that how you shop for a car? Now, what you really do, probably, is you say, okay, well, let me test drive that car. And then I'm going to go and shop around at some other cars, too. And then in the end, it's actually possible that I will come back and buy that car. But I would not feel good about buying that car having not looked at any others. But what's the difference between buying a car and designing a piece of software? I can only think of 2 real differences. One is that the possibilities for software are much broader and less well understood. So if I actually did buy that car, or indeed pick a car at random, the chances are that it would suit most of my needs. That's the truth. In 2019, I could pick a car at random, and it would suit 90% of the needs that I have. That's probably not true of a software design. The other thing is that most of the time, software development is quite a bit more expensive than buying a car. So both of those, though, would suggest spending more effort trying to choose a software model than we do a car. And specifically, I mean, looking at more alternatives, because there are lots of methods where people put a lot of energy into designing the software. But that energy doesn't usually go to looking at a broad range of alternatives. So somehow or other, we've got to get some alternatives in there. And if I've been listening to the way people talk, I realize that some people sometimes say that the cargo's itinerary is a series of stops, but sometimes they say that it's made up of a sequence of legs. So the cargo will, so a leg will be like, you know, the part that goes from Hong Kong to Long Beach, California on a particular ship. That's one leg. So maybe we should try that out. So I'm going to throw that up there too. Now this time, the conversation has to change. The shipping expert can't just say, that's good, do that. course, if legs had come first, that's what would have happened. But now it's more of a conversation about, well, why should I use one versus the other? Or maybe it will even trigger, I find that about 3, if you can get 3, it changes the way people think from sort of choosing one to realizing that they're just looking at examples from a very large set. And if you can get to that point where you have that shift in your mind, where you realize you're looking at samples from a very large set, it gets to be much easier to come up with more alternatives. But it's not so easy to get those first 3. I can do my little trick again. So for example, what I said earlier is that a cargo's itinerary is a series of legs, and I explained what a leg is. But let's just ignore the bubble on the right. Do the trick of comparing what I say to the more formal. In this case, it's just the diagram on a board. We don't have real software, but still, the diagram on the board has already diverged from the way I talk about it. So look at that for a moment. What is the difference? Can someone just point out a difference, any difference?
Location of location.
So the words, I mean, how do the words not correspond to the diagram? A cargo's itinerary is a series of legs, and I have that diagram, the lower one. So there are 2 differences, and I think I heard them both come from various people. One difference is that the diagram is less specific. It doesn't say that the legs are a series. It just says it's a collection. So we could fix that. And that's kind of a detail, though. I mean to say it would be a good thing to fix, but it isn't a fundamental change because the series is a collection. But the thing that really is missing is the word itinerary. That is, the statement doesn't say a cargo has legs. In fact, as an English statement, that sounds very weird. A cargo has legs. What sort of cargo has legs? Maybe we're transporting live animals or something. Or chairs. Yes, I'm transporting chairs, and my cargo has legs. Well, that's not what this means, though, right? That's a different sense of legs. So we need to really take seriously that we're not using the same language. And here's an observation I want to make. I've used the word itinerary in this presentation many times. But I don't think people were sitting there saying, well, why isn't he putting itinerary up as a concept to use in our model? You weren't thinking that. Nobody would think that because we're just used to hearing words and, we get the gist of what's being said. You get the meaning of what I'm saying, but not paying enough attention to the actual words themselves. And I think that if you pay attention to the words themselves, it gives you wonderful clues to models that can really help solve the problems in the software. So I'm going to add a couple more. One would be that a cargo would have an itinerary, and that itinerary would have a sequence of legs. And another would be that it would have a sequence of stops. I could do it both ways. So now I've got at least 4 distinct models and minor variations around those. And at this point, hopefully, we would have other ideas as well. So, but that's enough to get, I think, the sense of what I'm trying to do here. And notice that these diagrams are written in a very informal style. The point being that we don't want to invest a lot in these ideas at this stage. We want quantity, but not depth of analysis. We can do the depth of analysis later if we need to, but right now we want to get broad. That means, in fact, we need some ideas. We don't really have any in this picture, but we need some ideas that are just bad. You don't know if you've really explored the space of the problem unless, or rather the space of possible solutions, if you never come up with a bad idea. But because when I made this slide, I was too familiar with the problem, perhaps, or just too embarrassed to show a really bad idea. This isn't a good illustration of that principle. All right, so there's one of the things. You've got to generate some variation, but you've also got to keep moving. One of the things that happens to people doing software modeling is that they get, and this is the perfectionism again, they get into a loop of just doing more and more, spending time. If you're not getting good ideas, then move on to something else. Come back to it later. And don't be too finicky. I don't think you can really succeed in this if you have a group of people that's working on it where you will really be, where your prestige will be lowered by you putting up a bad idea. If you put up a model and everyone says, well, look, it's got the wrong kind of dependencies in it. And then you say, oh, well, I'm sorry, I'll go away and never talk again. If you're in that kind of place, this isn't going to work. So, now also, implicitly, I think I've said that there would be more than one session like this. I don't like these sessions to run on for hours and hours. An hour and a half is long enough. At that point, you're not going to have any new ideas. So you have to have multiple sessions. And then people get to the question, well, what do you document about this? This is meant to be low cost. So I would say that I would just look at the board and say, is there anything here worth remembering that we would want to feed into the next session? And the answer might be, no, it was a good discussion, but we don't need to keep any of this. And then you can just forget about it and schedule the next meeting and be done. Here, I think we did get some things. I would just say those 3 words would be sufficient. But maybe the diagram of the cargo itinerary stop would be good to have. That would be enough. And I might write those in my design notebook and just leave it at that. We don't have to have a wiki documenting every idea that we have. And now we have to move on. Now, at some point, you're going to have to decide, right? Generating variation is very important, but then you have to select from the variation. So it's a very different kind of thinking, different mode of thought, and also different criteria, and I think different people. So one thing that I think is important, too, is that you have different meetings, probably with different people, to come up with the ideas, or to select, or most importantly, to decide whether to actually use something. So that's really, I guess, 3 different kinds of things. But the most important is when it comes time to actually decide, and we're thinking about, oh, should we actually do this thing? Be sure to have a meeting where the stakeholders that would be affected are there. That might be the project manager. It might be another project manager from another team where your stuff is used. If you don't do this, the next time you try to have idea-generating meetings, you'll have all those people there, and you won't be generating very many ideas. Well, anyway, how do we choose a model? And I don't mean forever necessarily, but for now. So stops or legs, for example. Let's just boil it down to these 2. We're going to have a cargo with an itinerary with stops, or a cargo with an itinerary with legs, and just have a show of hands. Who thinks we should choose stops? And who thinks we should choose legs? All right, legs wins. I think this would be a better process than what we usually do. What we usually do is we'll have some document with a nice diagram in it, and then at some future time, a programmer will get a story card, and it will have, require some of this functionality, and they'll do it some way. That's about it. Or maybe they'll get the diagram with no kind of meaning, and so they'll make those objects, but none of the sort of kind of subtlety of the concepts will come through. So we can do better than that. But before we do, I want to talk briefly about what I mean when I say model, because I've used the word a lot of times, but I haven't really said what I mean. And there are a lot of meanings to the word model, and you guys know many of them. You can eliminate some of the obvious ones. Don't mean a tiny ship in a bottle. But there are, for example, people often say model, and they mean a UML diagram. And I've used a number of UML diagrams, but that's not what I mean. What I really mean is the concept behind that diagram. So if we look at a map of the world, we could say that this is a kind of model of the world. And yet, and it is, but still it's not quite the kind of model I mean. I mean the model behind this map. So take a quick look at the map and you can see things like, I don't know how big things are. You could say the United States and China look about the same size, and they actually are approximately the same size. Or you could look and see that Greenland and Africa are about the same size. So I suppose by extrapolation that they are the same size. Oh, I see someone shaking their head, so apparently they're not the same size. Here's a different map of the world. This one shows Africa and Greenland, and oh, I guess they're not quite the same size. In fact, Africa is 14 times bigger than Greenland, but they look the same size on that map. Now, is that because the people who made that map didn't know how big Greenland was? Or perhaps they thought, you know, this is my pet theory that got shot down by this XKCD comic, but my pet theory was that this map was made in the US. You can tell because it's right in the middle of the map. And so you know where it was made. And then there were some immigrants on the team that made the map from Greenland. And they said, Americans aren't very good at geography, and if we make Greenland huge, generations of Americans will think that Greenland is big. And so that's what happened. But actually, it turns out that's not what happened. The Mercator projection is the reason. Now, why, though, did the Mercator projection become so extremely popular? That turns out to be because it was very useful for a particular case, which was important in the 1590s when it was made, which is that if you make a map based on this projection, you can draw a line between 2 points, and that line the angle of that line corresponds to a compass heading. If you want to know what direction, you know, New York is from Lisbon, you draw a line between New York and Lisbon, and if you pointed a ship that direction and went in a straight line, of course you wouldn't do that, but it's a sort of starting point for a navigator. So this map was really made for use on ships by navigators. But then it was good enough to use for many other purposes. And sometimes you can even tell things like how big something is. You can tell that the US and China are about the same size because they're at about the same latitude. As long as something's at the same latitude, you can compare the size. If you wanted to, you could compare the size of Africa and Greenland by making an adjustment based on the latitude. It would be a more complicated calculation. So by choosing a model that is well suited for a particular problem you want to solve, you can make the computation simpler or more complex. This one makes figuring out directions very simple, but it makes figuring out the size of things a bit complex, but it's still possible to do. If I wanted to know the population of the US versus China, I could not do that with this map, no matter how complicated the calculation was. So there's these sort of factors. Now, what is the model as I mean it? Well, behind this model, behind that map rather, is the concept that the world is round. It's implicit in it, but that the world is round and that all we're interested in is the surface and certain points on that surface. We're not interested in the chemical makeup of the land or anything about the magma underneath. We're interested in where the coastlines are. So we need a way of describing that. a spherical coordinate system, such as latitude and longitude. And then we transform all our data into that form. Then we need to convert it into a flat map, or technically into a cylinder, because you could rotate that map. And we need to do this in a way, because there are an infinite number of ways of transforming a spherical surface into a cylinder, but we need to do it in a way that preserves the direction of 2 points relative to each other. There's only one way to do that, and it's the Mercator projection. This is the model. And if you take that model, if you look at the pieces of it, you see that here's an abstraction. This very complex and concrete thing, the Earth, is abstracted as this simple geometrical figure. And we aren't using all the data we have. We're using certain kinds of data. In this case, the location of coastlines and rivers and so on. Using another abstraction to represent it relative to the other. That is, latitude and longitude is meaningful in relation to a sphere. Then we need some math to do the transformation. Now, I don't know exactly how Mercator did it. Some kind of geometrical technique, I'm sure, with protractors and stuff. But the modern way of expressing it is this function, this projection function. And then we can make an assertion. And this assertion is where the power of the model comes from. I could take a different data set, and I could apply the same model, and I get a different map. This is Mercator's original map. This time, Europe is in the center. Specifically, Belgium is in the center because Mercator was from Belgium. But you can see that the map is essentially the same. A lot of details are different because their data set wasn't as good. But if you look at Europe and Mediterranean, the data is pretty good. You look over in North America, and the data's okay. South America, it's actually a little better on the East Coast. The west coast of South America is weirdly sort of shifted to the east. I think there's an offset error in the data. And the west coast of North America is kind of vague. It's like they knew there was a west coast, so they just sketched it in. We could call that an extrapolation or an interpolation of incomplete data. And boy, this starts to feel to me like the kind of things we do on software projects. We take a data set that is imperfect and incomplete. We apply transformations to that data that allow us to make meaningful decisions. The decision in this case is, which way should I point the ship? So the domain is just anything that you could know about. But the model is a system of abstractions representing some selected aspects of that domain. This is a very basic definition of model. But I think anytime we start to get more concrete, more hands-on than that, we lose the power of the model. The power of the model is that it is a set of concepts. But it's not neutral. It distills some assumptions and knowledge that we have. And some models are good for some things, other models are good for other things. This is not a way of representing reality. In fact, I think realism is a distraction. Consider, is this a realistic picture of the world? Well, we discussed, for example, that Greenland is not the size of Africa. Maybe this, then, is a more realistic picture of the world. Greenland and Africa are in their proper perspectives, but somehow the idea that, if you went east from Africa, you would just end up in space doesn't feel right either. So neither of these is realistic, nor are they trying to be. This is a pretty realistic picture of the world. If I were a navigator at sea, though, I would rather have either of those other two than this. And I would much prefer the Mercator map over the Dymaxion one, but I would settle for either rather than this very realistic picture. Realism doesn't give us models that we actually can use. Another thing about models is they need a narrow focus. I Googled for domain model and found this on the web. And I think there were some more complicated, but this was all I could really fit on a slide. Completeness really leads us off the track. And yet we say, but we have all this information. We have to represent it somehow. We have to get it into the computer. And yes, that's true. I could picture having a database where we just say this database is for archiving all the data we've got in some kind of canonical form. But that's not the kind of model I'm talking about. If you're going to do that, what you need to do then is have a separate representation of that, of some small selection of that data that will be used to solve specific problems in the domain. And you'll transform the data back and forth. And I think that is, in fact, a recommended thing. That is, we want multiple models for multiple problems within a larger domain. So a model should be focused on a specific, difficult, important problem. This is obviously too hard to do for everything. Don't do this for everything. Do it for the hard problems, the ones that you don't think you'd get right if you just started writing, well, if this, then this. If you think you could get it right doing that, then do that. But if you don't think you could get it right doing that, maybe a model would be helpful. And for that, then you need to say, well, then this model would be helpful for what? For a specific use, right? A specific kind of problem. This is one of the reasons that I emphasize concrete examples. Earlier I asked, which of these two models do you like better? That's not really the right answer, the question. The question I should ask is, which do you think would be more useful? And when I ask the question like that, it might cause you to change the way you're thinking and think, well, useful for what? What am I being asked to do at using this model? And then you might say, well, okay, we need some scenarios, some specific stories about the business that tell us what we're going to use this thing for. And I did tell you one. I told you the initial booking. And you might say, well, for that purpose, I think either of these would be fine. I could describe the result of the initial booking using a series of stops, an itinerary as a series of stops, or an itinerary as a series of legs. I don't think there would really be much difference. So let me give you another scenario, another thing we have to solve, and I think it can be, we can use the same model for both of these. Sometimes a customer will call up and say something like, I want to send my cargo to Dallas. Then a little bit later, they will say, oh, I want to send my cargo to Seattle, not to Dallas. But by this time, the ship has already sailed. The cargo is somewhere in the middle of the Pacific Ocean. If only they had called a few days sooner, we could have just done the whole thing over again, right? Then it's simple from a software point of view, because we can just undo everything we did and do it all from the beginning. But now we cannot do that. We need to do something to get rid of the legs. I mean, basically, this ship is going to go to Long Beach, California. And then is our next chance to change anything. Our cargo will be unloaded in Long Beach, and we could put it on something else. We don't want to put it on to the leg that goes to Dallas. So we want to cancel that leg and replace it with something else. Now, the way that I'm trying to explain the problem might lead us to think that the leg model might be helpful for this problem. Because it's so natural to talk about canceling a leg from Long Beach to Dallas and replacing it with a leg from Long Beach to Seattle. But I can do it the other way, and I will try, because it's worth looking at our alternatives. we could cancel the unloading portion of the stop in Long Beach and the stop in Dallas, merge the remaining part of the Long Beach stop with the load portion of the stop that sets the cargo bound for Seattle, and add a stop at the end that unloads in Seattle. That's not so bad. Here's a pseudocode version of that. And it is actually something you could do. This is not out of the realm of reasonable solutions, but here is the solution with the leg. And not only is it fewer steps, but each one is less confusing. It's not so much the number of steps here. It's how tricky some of those steps are, the ones that involve taking a stop apart, putting it back together again. In the leg-based one, we take things apart between, So, back to our original design. If we're going to transform this thing, it did look like this, and now it's going to look something like this. When you're still going to send the origin and destination to the routing service, but instead of updating the database, it's going to create an itinerary, pass that back. Notice that we now have rid ourselves of that side effect. The routing service no longer needs to update the database. I mean, someone could make it so that it updates the database, and I imagine they will if we don't communicate very well. But this is a great opportunity to improve the basic properties, the sort of architectural properties of the design. And it comes from having a very explicit way to talk about the results of this computation. Another thing we talked about earlier is the disconnected itinerary, remember? Now, previously we were putting integrity constraints in the database and stuff like that. But now that we have a little more way of describing the result of routing, we could talk about how this could be done in terms of this model. Does this model lend itself to telling you whether an itinerary is disconnected? I think there's a fairly straightforward way of doing it. So you could say that an itinerary is connected when the end location of each leg is the same as the start location of the next leg. That's very natural. You could talk about that with a business person and find out perhaps that that's not really what they mean, or find out that, yes, you've got it right. And that looks almost like pseudocode, right? You could say, yeah, I could code that. Now, it looks so much like pseudocode that I want to point out something. I don't mean when I say an itinerary is connected when, I don't mean I'm describing the calculation that you should do. What I'm really hoping to do is define a new word that will be part of our language and a new concept. In other words, I'm saying that the model is not just those three objects, a cargo, an itinerary, and some legs. It's not just those objects. It's also, it describes the way those objects are related to each other. So, for example, one of the properties that an itinerary might have is it connected? And that's part of the concept of an itinerary. It's not just a calculation that we can do, but it does correspond to a calculation we can do. Being able to step back from the calculation and say this is actually a concept, in that sense that I talked about what is the model earlier, that's a very key thing. We're not just rearranging the code in some way. When we get to this point, where we can talk about the solution that we have, talk about our software, the same way with another software person as we can with a business person, and where we can have real discussions with them about the things that need to be done and how we might do them differently. We call that the ubiquitous language. And the ubiquitous language is one of those fundamentals of domain-driven design. You can see throughout the whole example that I've emphasized language, looking at how we talk about the problem as being fundamental to finding a good solution. So ubiquitous language is one of those 3 or 4 concepts. One thing about that word, that phrase, ubiquitous language, is that it kind of conveys a ubiquitousness in all sense, that your whole system would revolve around one language. And that is emphatically not what we mean. So I like to append ubiquitous language as this within a bounded context. I'm not going to talk about bounded context right now, but Cyril will in a couple of hours. I can't remember exactly when he was in the agenda. So we'll go into depth on that concept. But the idea is basically that we will have multiple models with distinct languages, and that whole assembly of models will provide us with the solution to the various problems that we have. So getting back to the question of why do this stuff, I think that the answer lies in complexity within the domain itself. Sometimes we have complexity in the technical solutions that we need to do. Perhaps if we were, say, in the early days of creating Twitter, Twitter is pretty simple in its logic, but especially early Twitter was. But at the time, the idea that you would send out millions of messages in a timely way to someone's, to the followers, all those things, that was a real challenge at that time. Now, because of the frameworks that they created and made public, it's not actually that hard to do now. If I wanted to go create something on the scale of Twitter, I think I could do it all by myself. That probably couldn't get very many people to sign up, though. But the point being then that the Twitter of that time would not have met this criteria, right? The critical complexity that they were dealing with was a technical scaling complexity. Whereas most of the time on the projects that I've been working on, the critical complexity is in the domain itself. It is that shipping is very complex. And if we do our job right, our software might not actually be more complex than shipping itself. But if we are not careful, our software might be much more complex than the actual shipping domain. And because the actual shipping domain is probably pretty close to the minimum complexity that we can hope for, right? Well, that is basically my time, but I want to just touch on one other thing. Suppose that instead of presenting the scenario that I did as the second scenario where in mid-transit they changed the destination. Suppose instead I said, well, we're still on our original itinerary, but we're about to arrive at the first port, and we need to generate these purchase orders to tell the people in the ports how to actually unload the cargoes, what to do with each cargo. And there are these companies that operate in ports, and we need to figure out which one to send each instruction to, and we need to get the whole story of each of thousands of cargoes right, crisscrossing through an enormous, complex port. And when you look at this problem, you start to think, wow, the things that happen in the port are more complicated than the things happening in the routing of the ship. Maybe my model should be re-geared around that. And that might point me to the stops model. Because stop has a very explicit place to talk about the port. The stop represents everything that happens in a port. The leg says everything that happens between the ports. It literally has no place to put information about what's happening in the port. And so you would have ended up with a quite different model. It isn't like we're converging to the best model. We are converging to a model that's very path dependent, depending on the particular problems that we are trying to solve and the order in which we try to solve them and the ideas that happen to come up during that process. So if you encounter a different sort of problem later on, you have some choices. You could say, well, let's bite the bullet and change to stops now. And you're accepting that your solution to the routing problem will be slightly more complex. Remember I said, though, it's not out of the question, right? It's doable. But we'll reserve our best choices for the most difficult problem, which is the one in port. Or maybe this is time for two bounded contexts. I'll solve route-related problems over here with legs. We'll have another place where we can solve problems in ports using stops. And I'll have to transform the data back and forth, back and forth. But that's doable too. Or a third choice, which is stick with legs and go ahead and cram the new functionality on there somehow. You know, I can deal with the first vendor on the unload of the the incoming leg, and the last vendor on the outgoing leg. Then I'll just put all the other vendors onto the incoming leg because I've got to go somewhere. And that is also sometimes a valid choice, but especially worth mentioning because it is the default choice. That's the choice you make if you don't recognize that there's a choice to make. And that's a choice that gets made all the time. In fact, I think probably on most projects, it's sort of a time thing. How long is it before you make that choice? And once you've made that choice, you're kind of stuck because you have a model that no longer fits the most difficult problems you're trying to deal with. So you're not getting much benefit from modeling. And that's the last thing I'll say before I turn it over to the next person. Remember that having a model doesn't actually give you any advantage as such. The advantage doesn't come from having a model. The advantage comes from having a model that is a very nice fit to the specific set of problems that you are trying to solve in that context. If you have a model, no matter how nice its properties might be in an abstract sense, but it doesn't fit the particular problems that you are trying to solve, it will not give you any benefit. It might be fighting against you. So I'll go out on that point, and I hope that this example helped to illustrate kind of the spirit of domain-driven design, and I'll leave it to the other guys to go into the various more detailed parts of it. So, thank you.